Okay, so to begin with, we're going to have a look again at, first algebraically and then geometrically, how to find these complex points that a circle has in common with a line. So let's start with it algebraically. Let's say the circle is the unit circle, so it has equation x squared plus y squared equals 1. And let's say the line is a horizontal line at height h above the origin, so it has equation y equals h. And we're going to suppose that h is greater than 1. So the line has no real points in common with the circle. So if we solve these two equations here, then we find that the contact points of this circle and this line are going to have coordinates. Well, the x coordinate is going to be plus or minus the square root of 1 minus h squared, and the y coordinate is equal to h. So this thing here is a complex number, and what we're going to do is to try and understand how our geometric method, which we were looking at before, also gives us this kind of answer in a sense. So let's recall what our geometric method is. This is how to find the complex contact points of a conic and a line which doesn't have any real parts in common with that conic. So we start by drawing a perpendicular line from our black line that we're interested in through the centre of our conic. We find where that line meets the conic, and then we draw lines parallel to our black line at these meeting points, and we find out where this perpendicular meets our black line. Now that's going to give us the real components of the complex contact points. And so we still want to find what the imaginary components are. To do this, we get that point, we draw tangent lines, and then we get these 4 points where those tangents meet those lines parallel to our black line. We add the new lines between those newly found 4 points. There's 2 such lines. And then that gives us those 2 lines intersect our black line at 2 new points. And if we look at the distance, so we call those the amplitudes, they basically describe the complex contact points. If we look at the distance between one of those amplitudes and the centre, that basically tells us the imaginary component of our complex contact points. So in particular, if we think that these different points on this black line are given numbers, then we can associate this real point here, the real components of the contact points, with a number a, and if this distance here between a and this left amplitude is b, then we could say that the contact points of this line with this circle have the form a plus or minus b times the square root of minus 1. So since it's multiplied by the square root of minus 1, this second part here is the imaginary part, and this can be plus or minus. So in terms of standard complex numbers, you basically have two contact points and they are complex conjugates of one another. Anyway, let's have a look now at this from a more geometric standpoint. So what we're going to do is we're going to use a bit of analytical geometry to actually work out what this blue length is physically. So just for temporarily, let's stop thinking about the imaginary numbers and things and just look at this as a geometric construction, and we want to determine this blue segment length. So I'll just do it quickly. You may want to see if you can show all this for yourself. So this point here, this has an x coordinate of 0 and a y coordinate of h. If you solve for where the tangents from this point meet the circle, you find that they meet, for example, at this point here, which has an x coordinate square root of h squared minus 1 divided by h, y coordinate of 1 over h. Of course, there's going to be a contact point over here as well, which is going to be the reflection of this point here in the x equals 0 line. And then this line here, this is going to be the line where y equals minus 1. And this point here, you can work out that this has coordinates, well, the x coordinate 1 plus h divided by square root of h squared minus 1, y coordinates of course of minus 1. And you can also work out that this point here this has x coordinate of 0, y coordinate of 1 over h, and then you can get the equation of this line. And finally you can determine that this point here this has an x coordinate of minus the square root of h squared minus 1, which might seem familiar to you, and a y coordinate of course of h. Let me just put a line there to make sure those two don't look the same. And similarly, this is the reflection, so this point here has x coordinates square root of h squared minus 1, y coordinate of h. Now then, remember before that when we were using the kind of Cartesian algebra, we worked out that we should have that x is equal to the square root of 1 minus h squared. And I said to you that this method, this geometric method, will give you this distance here, or equivalently this distance here that I'll now draw, and that this will give you the size of the imaginary parts of these complex fixed points. Well, that makes sense because essentially what we found from here, oops, let me get back to the pen. what we found from here is that the imaginary parts of this, well, we found that x is basically equal to the square root of -1 times the imaginary part, which is going to be the square root of h squared minus 1. These two things are equal. And that's exactly what we have here. So basically, this geometric method gives us this distance here, which is the size of the imaginary components of the complex contact points, and it can be plus or minus. Okay, so now we've inspired a bit more faith in this construction as a way of determining the imaginary contact points of a conic with a distant point. We can think about what does the imaginary part of a conic look like? Now, there's an aspect of that question that's nonsensical, in that we can't really see these imaginary things. We can only see representations of them. But one thing we can do, which is quite useful, is we can get a conic, in this case a circle, and we can pick a direction, in this case the horizontal direction, and we can think about how this conic meets up with all these different lines in that direction. So we already know what happens when lines are overlapping with this circle at real points, but what we can do is move the line around outside the circle, and we can record the amplitudes of the complex points at which this line meets the circle for different positionings of the line. And what we see is that it sweeps out a rectangular hyperbola. So at any given place, the width of this blue line is telling us how large the imaginary part of these complex contact points are. So we can see, for example, that as the line approaches the circle, this contact point flips round from being two complex distinct contact points, in fact complex conjugates of one another, and then as they reach this point we get that those two complex contact points merge, and we have one kind of repeated real contact point at this place here where we're on the surface of the circle, when we're at the meeting point of the circle, and then in this intermediate region here this line has two real separate contact points with the circle, and then again we have a similar situation going on as we move the line further down, and again we get complex contact points again. And if you recall, last video we had a look at this issue of finding the common contact points of two circles. Well, what you could do to think about this is, if you find out where these different circles meet these lines, and you do it for all the lines which are perpendicular to the connectors of the centres of the two circles, well then you'll have these two different hyperbola which are exuding from your two different circles, and at the place where both of those hyperbola are the same width, that'll be where those two circles will meet each other at complex points. I'll show you a proper picture of something like that later. There's just one other thing though, which I think is very interesting. It's again something I'll come back to later, because I think it's quite a hard idea to... It's not technically complicated, but it seems very sort of non-intuitive. Imagine you keep moving this line further and further away from a circle. So as you do so, the amplitudes are going to get further and further away. Now, in the case where this line is infinitely far away from a circle, the amplitudes are also going to be infinitely far away from one another. Now the thing is that since we do think of this line at infinity as a definite thing, it turns out that for any pair of circles we have this situation where any two circles are going to meet the line at infinity at the same complex contact points. Because if you draw any other circle and make this same construction, again you'll have a rectangular hyperbola, and those two hyperbola are going to intersect at infinity, and there's going to be these two different complex conjugates of one another. In other words, something like a plus b times the square root of minus 1 and a minus b times the square root of minus 1. Those two contact points are going to be on infinity, and they are actually common points for every pair of circles. So not only do a pair of circles meet at a couple of finite real or complex contact points, they also always meet at a couple of infinite contact points. We're going to come back to this later and see that these 2 points, which are normally given the notation capital I and capital J, are very special sort of absolute elements, which if we give a distinguished role to them, we can then essentially derive or infer the rules of Euclidean geometry from the rules of projective geometry. So accepting these special imaginary points at infinity gives us a way to get back our familiar specialized Euclidean geometry from a more general system of projective geometry. So let's have a look at this general problem then, where we have a generic conic, say this ellipse through these 5 points, and a line, and we want to work out the complex contact points of these two objects. So the construction is very similar to before, but there are just a couple of subtleties. So the way we begin is we draw a line parallel to our black line, which just meets the conic tangentially, and we do the same again for the other tangent. So essentially what we've done here is work out the tangents from a point on this black line at infinity to this conic, if you like. And now if we rule a line between those two contact points of those tangents, this should give us our real part of the complex contact points of this black line and this black conic. And then basically the way we continue is quite similar to before. We draw tangents out of this black line to our conic. Maybe I'll just hide that so we can mark these out. In fact, there's no need. We find out where these tangent lines meet these parallel lines, and then we join up the corners of this quadrangle that we've made and see where these newly added lines meet our original. and these give us our amplitudes. So this central black point is the real part of the complex contact points, and this distance here gives us the size of the imaginary parts of these complex contact points. Okay then, so that's how this system works in this case. We can also again look at how the family of all of these parallel lines make these make different complex contact points, and we can visualize one of these sort of hyperbola showing us these different points. Now, since our ellipse here is not a perfect circle, in this case this isn't going to be a perfectly rectangular hyperbola, and so this is probably a little bit too complicated a thing to say at this point, but anyway, I'll say it nevertheless. Before I was saying that any two circles meet at these complex points at infinity. The same is not true of generic ellipses, because their hyperbola are not perfectly rectangular, so they don't meet this, they don't have these common points at infinity in the same way. Now what else we can do is we can take a look at some other shapes like a hyperbola. Yeah, suitable one. Okay, that looks like a good one to look at. Right then, so again we do the construction quite similarly. Maybe I can just begin it again. So to begin with then, we want to find out where the real part of the contact point is. So we can see that this line doesn't meet this hyperbola at any real points in this case. So we draw these lines parallel to it that are tangent to our hyperbola. One here, and again probably around there. I'll just make this hyperbola a bit sharper so that things are a bit clearer. Okay, so we have these meeting points of we have these two lines which are tangents from a point at infinity on this black line to this hyperbola. The green lines are tangents to such a point, and then joining those 2 points, they meet the black line at a particular point, and that's going to be the real component of the complex contact point between this black line and this black hyperbola. Then we continue as before. We draw tangents from the black points to the hyperbola, and then we see the 4 points at which that meets our parallel lines. We draw in the 2 new lines, and we find out where those meet our black line, and they're going to give us the amplitudes of these complex contact points. So there we have one. And now again we can have a look what the what the imaginary components are of this entire family of parallel lines. So if we move around this line, we can have a look what these contact points are. Of course, once you go higher than this point, the line has real contact points with the hyperbola, so there's nothing there. But if we move down, we see there's a really nice kind of symmetry to it, that visualizing the complex contact points, so visualizing, let's say, the imaginary part of an ellipse gives a hyperbola. Visualizing the imaginary part of a hyperbola gives an ellipse. So I think this is well worth it to do this for yourself, and if you like to have a look at the algebra, you might want to try and work out how this kind of imaginary part of a conic looks in terms of the original form of the conic. It's a very nice exercise to do. Okay, so it's possible to find a pair of conics, such as these ones here, that intersect with each other at 4 contact points. But in fact, I claim that every pair of conics has 4 contact points. Now, they may be repeated, for example in the case where these two have a tangent in common, in which case these would say that they meet at these 2 distinct contact points here, and they also meet at this point here twice in a sense. So that's possible. But there's also other cases, such as this one here, where these 2 conics have 2 real contact points, but they also have 2 complex contact points. And there's this case here, where these 2 conics have 4 common complex contact points. So we've already looked how to find where 2 distant circles meet, but now let's have a look at the more general issue of where 2 distant ellipses meet. Now, in order to do this construction easily, let's assume that we can find the tangent lines, which are tangent to both ellipses at the same time. So there's going to be 2 of them, something like that. So these are the 2 common tangents of these ellipses. And now we're going to label where these tangents meet these ellipses. Okay then, so once we've found these common tangent points, what we're going to do, we shall label the point that they meet at and call it O. Now, in projective geometry, there's a sort of mapping from the plane to itself called a homology. It's a special kind of projection, and it has 2 important properties that sort of define it. One is that there's going to be a special point O, such that every line through that point O is going to get mapped to itself. That doesn't mean all the points on that line are going to be fixed, but the points on that line always get sent to points on that line. So it has a sort of point of invariant lines, if you like, and that's O. And also it has a line of invariant points. So there's going to be a special line somewhere on the picture, such that if we take any point upon that line, then the set of all lines through that point gets sent to the set of all lines through that point. So our method then to find the sort of, if you like, the common chord, or the line at which these two ellipses have common imaginary points on, is going to be to construct a homology which sends one of these ellipses to the other. And this homology is going to have this special point O, and it's going to have a special line equal to the line we're looking for. So this homology maps one ellipse to the other, but it has this sort of invariant line which is common to both. So how do we construct it? Well, if we take a point on our first ellipse, we'll call it A, and we'll draw a line through A and O, and find out where it meets our second ellipse at one of the contact points. We'll call that A dash. Now, if we have a look at this line AX through A and X, well, the image of A is going to be A dash under our homology, and the image of X is going to be X dash. So the image of this line AX is going to be A dash X dash. And so those two lines are going to meet at a point, and this is going to be one of the points on our line. Similarly, AY and A dash Y dash again meet at a point on this line. So that's enough information for us to draw in this black line. And so this is what we can think of as the common chord, or a common chord, of our two ellipses. And what you can do now as a sort of exercise, well worth doing, is if you do the construction that I was just talking about, and you find out where this left-hand ellipse meets this black line at the complex points, and you do the same for the right-hand ellipse and the black line, you should find that the contact points are the same. Now, I did say that there are 4 contact points that these two ellipses have with each other, so this finds 2 of them. It finds 2 conjugate complex contact points. Now, how do we find the other 2? Well, if we go back, we made a choice. Okay, so we decided already that this was point A, but we also decided that this was going to be point A dash, and we had 2 choices there. So if we instead decide that this is A dash, and we repeat the construction, then we'll get a new common chord between these 2 ellipses. So let's do this now. So again, we find out where AX and A dash X dash meet. That gives us 1 point on the common chord. Similarly here, AY, A dash Y dash. And so the other contact points these 2 ellipses have in common are imaginary points on this, are complex points on this line here, this black one. And again, you can check that with the previous method.